Okay, for what we have in number 27, okay, we're going to have a nonlinear Bernoulli equation, but I just want to stress once again for this problem that we do not have a homogeneous equation, and we start out with 3x y squared times the derivative y prime or dy over dx is equal to 3 times x to the fourth plus y to the third, and dividing by 3xy squared, and we have the derivative set equal to, and upon simplifying, okay, we have x cubed over y squared plus y over 3x. And now if I had like degrees between what we have in x and y for the first term, I would have a Bernoulli equation, okay, but for what I have instead, like if I had like a match between what we have for x and y, if I had like x cubed over y cubed, well, this would be the reciprocal of v cubed, whereas for y over x, we do have matching degrees where I would have otherwise had 1/3 of v. And if I had like x to the second over y to the second, this would be 1 over v squared plus 1/3 of v, and that arranged. So if I had like degrees in x and y for the first term, I would have had a homogeneous equation. But for what I have instead is a nonlinear Bernoulli equation. So we have in the rewrite, okay, setting things up where I can provide an integrating factor and setting things up along the lines of v substitution. Again, I have dy over dx minus the reciprocal of 3x times y is equal to x cubed over y squared, and just stressing the degree on the right hand side in y. So we have the reciprocal of y squared, so we have x cubed times y to the negative 2, so we have that n is equal to negative 2. And just taking some of the items that we have here, and we've got, again, so we have for p of x, we have minus 1 over 3x, and our q of x, again, we have what is multiplying y to the negative 2 or the reciprocal of y squared, so that is going to be x to the third. And again, we have n equal to negative 2, and once again we have with 1 minus n, we have 1 minus negative 2, and so that will come out to 3. And I'm going to get a bit redundant once again, and setting things up in terms of the substitution variable v. So I'm going to have, once again, I have v is equal to y to the 1 minus n, again, where we have n at negative 2. So y to the 1 minus negative 2. So that will come out to y to the third. Okay. So we got that v is equal to y cubed, and rewriting in terms of y equals, so taking the cubic root of both sides, so I have that y is equal to v to the 1/3, and just taking the derivative with respect to x on both sides. So we're going to have dy over dx is going to be equal to 1/3 of v to the negative 2/3 dv over dx. And rewriting this form in the nonlinear Bernoulli equation in terms of the substitution variable v. Okay, so we've got dy over dx, and so plugging in and substituting, so I have 1/3 of v to the negative 2/3 dv over dx. minus, and I have 1 over 3x, and I have times y, which we have at v to the 1/3, and I have is equal to x cubed over y squared, or in this case dividing by v to the 2/3, or multiplying by v to the negative 2/3. And I want to put the first term at dv over dx. So I'm going to take care of the 1/3 multiplying by 3 and v to the negative 2/3 by also multiplying by v to the positive 2/3. Okay, so multiplying the equation by 3 times v to the 2/3. So I'm going to have in the rewrite. Okay, so the first term we have dv over dx, and we have minus, okay, 3/3 is 1, and we had the reciprocal of x, and v to the 1/3 times v to the 2/3 is going to be v to the first. Okay, so we have minus 1 over x times v, and we have is equal to 3 x cubed. Again, v to the 2/3 times v to the negative 2/3, those will take care of each other. And so we have in the rewrite, in terms of the substitution variable, and so we got for setting the stage for the integrating factor. Okay, so this time we're going to have rho of x is equal to negative 1 over x. And for the integrating factor, for what we have in the equation in terms of the substitution variable v, so you have e to the rho of x dx, and that is equal to e to the integral of negative 1 over x dx, and that is equal to e to the negative of the natural logarithm of x. And again, we can go from coefficient to exponent, where we have e to the natural logarithm of x to the negative 1, and so we have, with the integrating factor, we can say that we have x to the negative 1, or the reciprocal of x. And so what we have in the substitution variable v, if I multiply this equation by the integrating factor, so I have 1 over x. Again, you can distribute, but again, I'm going to compact what I have on the left-hand side. And 3x cubed times 1 over x. So this is going to become 3x squared. So for what we have on the left-hand side, okay, and we're going to have, again, left-hand side, if I were to distribute, okay, well, I would end up with the product rule result of taking the derivative in x of multiplying the integrating factor, which we have at 1 over x, times the dependent variable, which I have momentarily at v, and this is equal to 3x squared, and looking at integrating over both sides. Okay, so we'll have v over x is equal to the integral of 3x squared dx. So we have v over x is equal to x cubed plus c, and isolating v. So we have multiplying by x, so we have x to the fourth plus cx, and again v originated upon substituting for y to the third. And putting back, so we have y cubed is equal to x to the fourth plus c times x. And if I lowered this all the way in terms of y equals, so this is going to be the quantity of x to the fourth plus cx all raised to the 1/3 power.